A common misconception is that hydrogen is always a carbon-free energy carrier. While it is true that reaction of hydrogen and oxygen don't produce CO2, we have to remember that hydrogen is not a primary source, so the environmental impact depends on the method of production. Scientists have color-coded hydrogen based on the production technology. Gray hydrogen is produced from fossil fuels, like natural gas or oil, through a method called reforming. So this is the least sustainable solution. Blue hydrogen is a step towards sustainability because we couple the process of producing hydrogen from fossil fuels with carbon capture and storage. So the CO2 produced is captured and stored away instead of being released into the atmosphere. There are two colors that are associated with carbon-free hydrogen, and those are pink and green. Pink hydrogen is produced via water electrolysis, powered by electricity that comes from nuclear power, while green hydrogen is produced either from biomass or from water electrolysis powered by renewable electricity. So it is the only true renewable hydrogen. There are two main production pathways under the radar today. And one is the method that is mostly used today, which is reforming of fossil fuels. This is the most common method for hydrogen production currently because it's quite cheap. This process is called steam reforming, when steam is the medium. It is used to extract hydrogen from hydrocarbons like methane or other hydrocarbons. And it consists of two stages. In a first stage, methane or the other hydrocarbon reacts with high temperature steam over a catalyst, usually nickel. The products of the reactions are hydrogen and carbon monoxide. In a second stage, the carbon monoxide reacts further with steam and produces hydrogen and CO2. Overall, we need to supply energy for this process, and the energy loss is about 15 to 20% of the energy content of the produced hydrogen. This is because we need to heat the steam at very high temperature, above 700 degrees centigrade, and we need to heat a reasonable amount of steam to guarantee that all the reactions can be completed. In fact, if there is not enough steam, at those temperatures, the methane and the carbon monoxide would decompose and the carbon would deposit on the surface of the reactor, inhibiting the catalyst. As of today, this is the most common hydrogen production way, and mostly natural gas and oil are used as primary sources. Water electrolysis, on the other hand, is seldom implemented because of still very high cost. Nonetheless, it's the other production technology that is worth mentioning because it can enable true renewable hydrogen production. So it is very promising. Electrolysis occurs in a device called electrolyzer, where the water molecules are decomposed into hydrogen and oxygen when we apply an electrical field. An electrolyzer has two poles, a positive and a negative pole, like a battery. And when we apply an electrical field between these two poles, we enable a flow of electrical charges. So electrochemical reactions can happen inside the water, and the hydrogen molecules can be liberated from their chemical bonds. There are two technologies nowadays that are very popular for water electrolysis, and those are alkaline electrolyzers and PEM, or polymer exchange membrane electrolyzers. Alkaline electrolyzers use an alkaline solution as a medium, while PEM electrolyzers use a solid polymeric membrane. and therefore they're more compact and they're also more suitable for intermittent power supply. So it can be very interesting for coupling electrolyzer with intermittent renewable energy sources like wind and sun. The cost of both technologies today is very high because they use rare materials like platinum. But projections for the future see that there can be reduction in the manufacturing cost and also possible reduction in the electricity price, making this solution maybe more convenient in the future than reforming of fossil fuels. The efficiency of this process for hydrogen production is around 70 to 80%. There are also other technologies, other investigation for electrolysis. One example is solid oxide electrolyzers. Those are ceramic electrolyzers and they operate at much higher temperature, 800 degrees Celsius or higher, and they're more efficient than their little cousins, the low temperature electrolyzers. So when we have a process that produces a high amount of waste heat, this could be coupled with solid oxide electrolyzers. So process cooling and hydrogen production could happen simultaneously. That would be very convenient. Research is ongoing also regarding other methods of hydrogen production from biomass. In fact, hydrogen is available also in a lot of other sources, biological sources especially, for example, in agricultural residues or other biological waste. And it could be extracted through several chemical or biological processes. So in the future, we may hear more about biomass gasification or biological separation for hydrogen production. But what makes one method preferable than another? Well, there are several factors that we have to consider. And one is the pressure at which the hydrogen is produced. Storing hydrogen is a serious challenge because hydrogen is extremely light, and so we need to compress it to very high pressures in order to store it in reasonable volumes. So the pressure at which it's produced, it plays a role. When it comes to electrolysis, PEM electrolyzers are preferable because hydrogen can be produced already at a higher pressure than alkaline electrolyzers. Another factor is electricity availability. Methane reforming doesn't require high amount of electricity, besides just to power pumps and auxiliary devices. But all of the energy that we have to supply is in the form of heat, so we can supply it just by burning some of the natural gas, the same natural gas that we use to produce the hydrogen. So in principle, it's a kind of self-sustaining process that we can implement everywhere. But water electrolysis requires a high, really significant amount of electricity, roughly 40 to 50 kilowatt hour per kilogram of hydrogen produced. So we need to consider whether we have the capacity to produce hydrogen from electricity in certain locations. And cost, of course, matters as well. Currently, electrolysis is simply not cost competitive if we compare to other alternatives, at least as long as there is affordable natural gas. But in those locations where natural gas cannot be supplied and where there is abundance of solar and wind energy, then electrolysis can also be a competitive solution. Tables can turn. It's very hard to predict what the future will bring, what will be the electricity price in the future. But definitely we can see that water electrolysis will become more important and more popular as the renewable sources like sun and wind will grow.